Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Cenozoic Earth history, focusing on the Quaternary period. So now we're going to start thinking about the onset of the Ice Age. Now around 40 million years ago, so that's going to be the Eocene, we begin to notice a decrease in ocean surface temperature at high southern latitudes, while we see deep ocean temperatures decreasing globally. Now, the decrease in ocean temperature at high southern latitudes, so that's towards the South Pole, was likely driven by the completion of the Antarctic circumpolar current. So this begins to form as the Drake Passageway opens up between South America and Antarctica, and so this means essentially Antarctica is now completely isolated and the seawater can circulate freely along its coast. Now, the formation of the Antarctic circumpolar current essentially surrounds Antarctica with a band of water which is constantly circulating around. This water tends to be quite cold and it doesn't mix extensively with warmer waters to the north. So it doesn't mix that much with the waters of the South Pacific, the Southern Indian Ocean and the South Atlantic. And so this means we have this isolated band of cold water which is moving along the coast of Antarctica, and this is actually going to help to keep Antarctica artificially cold. Now, if you remember, after the breakup of Pangaea, the world's oceans were kept artificially warm by warm waters which were moving from the tropical Tethys Ocean into other ocean basins like the North Atlantic. Now, by the Oligocene, so about 28 million years ago, we begin to see this flow of water from the Tethys Ocean into the North Atlantic in particular begin to be constricted. So we see it getting weaker, and obviously this is going to cause ocean temperatures in the North Atlantic to begin to decrease because this warm water is no longer coming in such large quantities. And then by the time we make it into the Miocene, we begin to see that this warm water flow has completely stopped. And so what we can see is as we're progressing from the Eocene into the Oligocene and the Miocene, we can see slowly but surely global ocean conditions are getting colder. And this is especially true in the North Atlantic in particular. So here's our situation in the Eocene. So you can see this area here represents what's left of the Tethyan Ocean. We obviously have the Indian Ocean seafloor down here, but the water in this area is going to be quite nice and warm. And so what we can see is that the warm water has the capacity to squeeze in the gap here between Europe and Africa to enter the North Atlantic and then move from the North Atlantic via the Caribbean into the Pacific, and then from the Pacific back into the Tethys/Indian Ocean basin over here. And so what you can see is this allows this warm water to circulate freely, and that's going to help to keep the Atlantic and to some degree the Pacific a little bit warmer than they would otherwise be. Now, by the time we make it into the Miocene, that's 14 million years ago, we can see that Africa has now made contact with Europe, and we can see that South America and North America are very, very close to completing contact. And so this means that at this point, of course, we no longer get this flow of warm water from what is now the Indian Ocean into the North Atlantic, and we don't get the flow of warmer water from the North Atlantic into the Pacific. And so this now means that these bodies of water are going to be operating essentially in semi-isolation from one another. And so we can see that if we look at this map down here at the bottom, we can see that once the continents reach their current position, we end up with the North Atlantic up here, the South Atlantic down here, the Indian Ocean over here, North Pacific, South Pacific, and the Antarctic circumpolar current down here. And each of these bodies of water are going to operate to some degree independently of one another, and so they're going to set up their own environmental conditions. But the most important thing is that once we begin to see this flow of warm water from the Indian Ocean slash Tethyan Ocean begin to decrease, we begin to see changes in global ocean temperature, and this is going to encourage the glacial event to occur eventually. Now, by the middle Miocene, so 14 million years ago, the Antarctic circumpolar current and decreasing global temperatures allowed an extensive Antarctic ice sheet to form. So this is in the southern hemisphere. And this helps to further accelerate the cooling of the southern oceans, because all of a sudden Antarctica was covered in ice. This ice is going to reflect solar radiation back into space, and so that's going to help to drive down the temperatures in the extreme southern hemisphere, so towards the South Pole. Now, after a brief warming trend that's seen in the Pliocene, we begin to see glaciers forming in the northern hemisphere around 2.8 million years ago, and this marks the start of the Pleistocene and obviously the onset of the most recent ice age. And we can actually see a picture here showing you the predicted extent of the northern ice sheets during the Pleistocene. We can see that obviously, all of Canada's under ice, a good amount of the northern states of the US. We can see obviously Scandinavia, and a large amount of northern Europe is under ice, and we can also see a substantial portion of Asia is also under very, very thick ice sheets by the Pleistocene. So now let's think about the climate in the Pleistocene and the Holocene. So the decreasing global temperatures that we see during the Cenozoic was not a rapid affair. Instead, it's part of a gradual decrease in global temperatures that starts all the way back at the Cenozoic-Mesozoic boundary and carries on through to the present day. Now, if we come over here, we can see a graph that's demonstrating this decrease in temperature throughout the Cenozoic. So we can see that we had the highest Cenozoic temperatures over here at what's called the end Paleocene thermal maximum, which is this point right here. You can then see we have a bit of a decrease in temperature. We then have a bit of an increase, which is called the Eocene climatic optimum. And then from that point on, we have a steady decrease in global temperatures. Now, this decrease isn't smooth. As you can see, there's quite a lot of topography here, but on the whole you can quite clearly see the trend has been for decreasing global temperatures over time. Now, the thing you'll notice about this particular graph is that it doesn't actually have any temperature values over here. Instead, we're looking at the delta oxygen 18 values. So if you remember, glacial ice will preferentially lock up water molecules that contain oxygen 16. Now, this means the oxygen 16 bearing water will not be returning to the oceans, and so this means as there's more and more glacial ice, more and more oxygen 16 gets locked up, and so we see a comparable increase in the amount of oxygen 18 bearing water in the oceans. And so when we have more ice, we have more oxygen 18 in the oceans, and so this leads to an increase in the delta oxygen 18 value. So what we can see is as the global temperature has been dropping, the delta oxygen 18 has been increasing, and this is telling us that more oxygen 16 bearing water is being locked up in glacial ice. So this is showing us essentially we have more and more glacial ice as we progress towards the present day. Now, this data is also useful on smaller timescales. So we've already discussed how sedimentary cores, which cover the last 2.6 million years, have shown us that during the last ice age we had 20 warm-cold cycles. So if you remember, during the cold portions, obviously the glaciers will be expanding, and in the warm periods, which we refer to as interglacials, we will have a retreat of the glaciers. In terms of temperature variation between these 2 points, it could have been anywhere up to about 10 degrees Celsius, so there would have been quite large swings. Now, you won't be particularly shocked to hear that areas that were proximal to continental glaciers or ice caps experience short, cool summers and long, wet, cold winters. And, this isn't a huge surprise. I mean, if you're living next to a giant block of ice, it's obviously going to have a very serious effect on the local climate. Now, as ocean temperatures were lower during the Ice Age, and the air temperatures were also lower, the amount of evaporation from the oceans actually decreased a bit. Now, what this meant is it actually caused the global climate to become drier. And this is simply a reflection of the decrease in the amount of water leaving the oceans and entering the atmosphere. Now, the other thing that we note is the compression of the temperate zones. So at present, temperate zones cover a large amount of North America, Europe, and a fair amount of Asia. Well, those areas which are now temperate zones would have been under or very near the edge of the ice sheet, and so we've already discussed that would have pushed the temperate zones southwards towards the equator. Now, this movement of the temperate zones towards lower latitudes, towards the equator, essentially led to increased rainfall in areas which we would now consider to be quite dry. So it meant that areas like the Sahara or the southern US states like Arizona, New Mexico, Texas would have had much higher rainfall. And this would have led to, quite substantial forest growth. Now, in North America, we have a constant high pressure zone which falls over the northern ice sheet. And of course, the northern ice sheet is covering pretty much all of Canada and a lot of the northern US states. And so this high pressure system which was sitting over the ice sheet essentially meant that if any storms tried to move northwards, they would hit this high pressure system and they would essentially get forced back down towards the southwest. And this forcing of these storm systems back towards the southern US meant that once again we have very, very high rates of rainfall in areas like Arizona, New Mexico and Texas. Of course, we know those areas would have had quite a nice temperate climate, and so conditions would have been absolutely perfect for the development of large forests. Now, another tool that's proven useful in the study of the climate during the Pleistocene and Holocene, especially during the Holocene in fact, is pollen analysis. So if you remember, pollen are the male reproductive units released by plants, and they get blown about by the wind. Now, the great thing about pollen is that they have a thick waxy coating, and this helps to protect the pollen. And so the pollen can be incorporated into sediments, and we can come along later, extract the pollen, and we can actually identify individual plant species from the pollen grains. So we can say, right, what plant species were present? And then we can say, right, what percentage of the pollen did this plant species represent? So it not only tells us which plants were there, but it also tells us how important certain plants were to that environment in that particular area. Now, in terms of the pollen itself, we can find pollen building up in sediments related to river systems, lakes, swamps, bogs, and even near-shore marine environments. So there's lots and lots of different types of sediments from which we can extract these pollen grains. Now, if we look over here, we can actually see an example of how we are using pollen grains to infer climatic change throughout the last, in this case, about 15,000 years. So this is for the Chatsworth Bog in Illinois. Now, if you remember, the transition from the Pleistocene into the Holocene occurs about 12,000 years ago. So down here at 12,000 years, this is where we're going to get the transition, essentially the end of the last ice age and a movement into more modern conditions. So what do we see? Well, we can see to begin with here between about 14,000 and 12,000 years, we can see we have lots of spruce pollen. Now, spruce is a type of tree that we get in the boreal forests of Canada. It's a coniferous tree, and so it's a conifer, and it's designed to live in cold conditions. So the large amount of spruce pollen, especially 14,000 years ago, obviously shows us that the Chatsworth Bog area in Illinois was a forested area, but it was very, very cold. So think of the coniferous forests of Canada, Russia, Scandinavia as an example of the kind of conditions we'd be looking at. Now, what we can see between about 13,000 and 12,000 years ago is we have an increase in ash. So ash is a deciduous tree, and so it tends to like to live in more temperate climates. It's not designed for cold weather. And so what we can see is the increase in ash is associated with a decrease in spruce. And so this is showing us that the climate in the area around the Chatsworth Bog is getting warmer. So we can also see the increase in ash was then also followed by an increase in elm and an increase in oak. And so these three together, these green lines, are representing the kinds of trees you would get in a deciduous forest in a normal temperate environment. So these trees make up a large amount of the forest trees which you would get in areas such as the United States, Europe, and also certain parts of Asia. Excuse me. And so this is showing us a clear warming trend as we essentially leave the last ice age, which was around 12,000 years ago. Now, you'll notice that the amount of ash decreases because it starts to get outcompeted by elm, and it also starts to get outcompeted by oak. So we can see that over time ash spikes, then it starts to become less important. The elms begin to outcompete the ash, but then they start to get outcompeted by the oak, and so it's the oak that really starts to take over and become the dominant tree in the area. Now, a thing that we begin to notice is around 9,000 years ago, we can see there's a sudden increase in grasses. We can also see we have an increase in ragweed and goosefoot. So these are the kinds of plants which we would expect to find on more heavily grassed areas, you know, like plains, for instance. Now, the increase in grasses, ragweed and goosefoot is associated with a general downward trend in the amount of oak. And so this would suggest about 9,000 years ago we have a change in the climate. So yes, things are still temperate, but conditions are clearly getting a little bit more difficult for these forests. And so we begin to see the oaks dying back a little bit. And the oaks are dying back and they're being replaced by grassland instead. So the amount of forest is decreasing and the amount of grassland is increasing. Now, there could be a couple of reasons for that. It could be a climate related factor. So things could be getting a bit drier. So grasses tend to do better in slightly drier conditions than trees like oak would. Or there could also be a human factor involved. Maybe this could be related to humans affecting the environment. So maybe we're cutting down oak trees and replacing them with grassland. So that's also another possibility. The most likely explanation is that it is a change in the climate. However, you can't definitively prove that. So what we can see is around 9,000 years ago, there's a steady decrease in the amount of oak, which is probably related to a slightly drier climate. And then we can see that the oak actually increases again at the end there. So what we can see is that there's been a steady change in climate, and we can use the pollen to crudely analyze these changes. Now, in terms of actually getting the pollen, we'll recover the pollen from the sample, we'll identify the plant species, and we'll simply use the principle of uniformitarianism to infer the climate. So, for instance, we know the conditions that modern spruce trees grow in, and so we can therefore infer the climate based on the presence of the spruce pollen. Now, when we combine pollen analysis with tree ring analysis and glacial sediment mapping, the pollen diagrams produce a substantial quantity of information about the climate, particularly in the northern hemisphere during the Holocene. And pollen analysis is absolutely great for the Holocene in particular. Now, the data indicates that there's actually been a relatively continuous warming pattern until around 6,000 years ago. So the Ice Age ends 12,000 years ago, approximately, and we see conditions getting warmer, and that makes sense. So this general warming trend keeps going for about 6,000 years. Then about 6,000 years ago, we see that there is a bit of a change in the climate. So at this point, we see the climate in the northern hemisphere becoming cooler and more humid, and this favors the growth of valley glaciers. And so we have a general glacial retreat from about 12,000 to 6,000 years ago. And then about 6,000 years ago, we then have a slight change in the climate that begins to encourage glacial growth in mountainous terrain. Now, the episodes of glaciation occurred during this what's referred to as a neoglaciation. So this slight change in climate, this slight decrease in global temperature, produces a small glacial event which we simply refer to as a neoglaciation. So it's not part of the Ice Age, it's its own individual, separate, small glacial episode. Okay, so now of course we actually need to think about the formation of glaciers. Now, during the Pleistocene, all types of glaciers, so valley glaciers, ice caps and continental glaciers, were far more widespread and extensive. That's not a huge surprise. Now, at present, we only have two continental glaciers, the ice caps that cover Antarctica, so should I say the continental glaciers that cover Antarctica and the continental glaciers that cover Greenland. But during the Pleistocene, we know that approximately 30% of the Earth's surface was covered in ice sheets, and now at present it's about 10%. And most of this coverage was located in the northern hemisphere. And we've discussed that's because in the northern hemisphere you had continental crust in the form of North America, Europe and Asia located quite close to the North Pole, and so that this made it easier for glacial ice to form on this nice solid stable continental crust, and so it actually helps to aid in the formation of large glaciers. Now, we also know these glaciers advanced and retreated several times during the Pleistocene, and this produced much of the topography formed in glaciated areas. So typically a lot of the topography you'll see in places like Canada and Scandinavia is the result of the movement of ice during the last ice age. Now, at the same time, we also have cooler temperatures which encourage the growth of valley glaciers within mountainous areas, and so we not only see a change in the size of the ice caps and the continental glaciers, we also obviously see an increase in the number and size of valley glaciers during the last ice age. So none of this is particularly surprising. Now, in terms of glacier formation, it's actually a relatively simple process. Now, if we have an area that receives more snow in cooler periods than melts in warmer periods, then we have a net accumulation of snow over time. Now, once this snow accumulation occurs, the snow at the bottom of the pile will obviously be compressed by the weight of the snow above it. And when you have enough snow, it's going to compress this snow at the bottom, and it's going to form glacial ice. Now, this ice will begin to flow in response to pressure, and you need to get to about a depth of 40 meters or so of cover before the ice will start flowing. So once you've managed to compress the snow enough to form the ice is just going to sit there until you have about 40 meters of material above it. And at that point, the weight of the 40 meters of material above it will be pushing down on that ice at the bottom so hard that it will actually cause the ice to flow, a bit like water. Now, the glacier will flow from this area where we're building up ice and snow, which is called the zone of accumulation. And in this area, we obviously have a build-up of snow occurring quicker than we lose snow. Now, the glacier itself will move downhill, typically under gravity, and it will move down until we hit the zone of wastage. So at the zone of wastage, we have a changing condition. So in the zone of wastage, we have a net loss of ice and snow. So we are melting more snow than is being deposited in those areas. And so obviously, once the glacier makes it into the zone of wastage, it's going to start melting, and as the ice melts, it's going to start dropping sediment. Now, as long as the glacier has a balanced budget, so the losses do not exceed the addition or vice versa, the glacier won't actually change in size. It will essentially be in equilibrium. Now, if there is some kind of change, such as conditions get warmer, and so we start to melt more of the glacial ice, we'll see the glaciers retreat. If conditions get colder, so we get more ice and snow being added to the glacier will obviously advance. And of course, as I'm sure you know, over the last few hundred years, we've been seeing a general increase in global temperatures, and this is associated with a generalized retreat for most glaciers. And of course, we know this is due to global warming, which is caused by human beings burning fossil fuels. So this diagram summarizes the general trend. So we have the zone of accumulation here. This is where we're building up ice and snow. Obviously, the snow gets deposited, it gets compressed, and eventually that compressed snow will form glacial ice. The glacial ice will begin to flow once we have a minimum thickness of 40 meters, and the glacial ice will naturally flow downhill under gravity. And it will flow downhill until it enters the zone of wastage. This is the point where the ice is melting faster than it's being replenished by new ice and snow, and so at this instance, this is where the glacier starts melting. This is where the glacial ice obviously disappears because it's becoming liquid, so it moves away in the form of river water, and obviously the sediment that's contained within the ice will be deposited in the form of glacial till at the nose of the glacier. So what are the effects of glaciation? So massive glaciers moving across the Earth's surface will reshape the previous topography and produce some distinctive glacial landforms. So remember, glaciers are big, powerful geologic events. They have the capacity to erode and move large amounts of material. So the movement of a glacier through an area is going to have a very significant effect on the topography of that region. Now, it should also be remembered that the effects of the Ice Age were not limited to glaciers. Obviously, we also have things such as large glacial lakes forming, which are a reflection of all this glacial ice. We also have the formation of large rivers associated with the melting of the glacial ice. But most of what we're going to talk about is a direct effect of the glacial process. Now, the expansion and the retreat of the ice sheets produced marine transgressions and regressions. This isn't a huge surprise. The more water you lock up in ice, the lower your sea level is going to be. And of course, when that ice melts, that water is going to return to the ocean basins and we're going to have a sea level rise. We can also see that mass glaciations drove changes in climate, both locally and globally. And we can see that when areas were once covered by thick glaciers, we can see this ground is actually currently rising. Now, this is due to something called isostatic rebound. So if you imagine a situation where you have a 3-kilometer thick ice sheet sitting on the continental crust, well, this 3 kilometers of ice is going to weigh a lot. And so the weight of this ice is literally going to be enough to push down the crust. And so when the ice is on the crust, the weight of it is going to push the crust down. And then once the glacier melts and retreats, the crust is going to bounce back up, a bit like a trampoline. Now, the thing is, this process isn't quick. So even though the last ice age ended 12,000 years ago, there are still areas of the Earth's surface which are rebounding back upwards. So this is called isostatic rebound. Okay, so let's start with some glacial landforms. So continental glaciers will produce things which we refer to as ice-scoured plains. And ice-scoured plains have little to no soil. They have a subdued topography, so essentially they're flat, and this is the result of the erosion of topography by glaciers and the deposition of sediment. So if we have any topography, it can be eroded away by the movement of the ice, and if we have topographic lows, they'll typically fill up with glacial sediments, and so this will produce a relatively flat topography. We can also see in these ice-scoured plains we have polished and striated bedrock. This is the result of the glacier moving through the area and stripping off the topsoil, because as we've already discussed, the glacier will sit directly on the bedrock. And because the glacier essentially planes the area flat, it means there's very little topography in the area. So that means there's, the gradient's very, very low, and this means water will not drain very quickly from these areas, because of course, in order for water to move, you require a gradient. Now, in terms of valley glaciers, we can see that valley glaciers produce a couple of distinct features. The first one is a bowl-shaped depression on mountainside, which are referred to as cirques. And the other feature that we notice are broad U-shaped glacial troughs. So these essentially are the valleys through which the alpine or mountain glaciers were moving. So we can also see that glaciers will deposit large amounts of sediment. So both continental glaciers, ice caps and valley glaciers will deposit large amounts of glacial till. And the vast majority of this glacial till will build up along the margins of the glacier, and it will form something which we refer to as a moraine. So a moraine is a linear body of glacial till that's built up along the glacier's edge. Okay, so let's look at some pictures to demonstrate what we're actually discussing here. So here's our basic model. So here's our continental glacier. And as we know, our continental glacier is going to essentially plow through the area. Now, notice that underneath the glacier right here, we can see there's no soil separating the glacier from the bedrock. Where there isn't the glacier, we can quite clearly see we have sediments. Now this means, of course, the glacier is going to be directly on top of the bedrock, and so that means that bedrock is going to be polished and striated due to the movement of the glacier. Now along the edge of the glacier here, we're going to have the ice melting. This is where the glacial till is going to be deposited, so this is where we're going to form our moraine. Now, once the glacier retreats, what are we going to get? Well, we're going to have our ice-scoured plains right here. So this is the area that's been planed flat by the glacier. And of course, as you can see, there's going to be relatively little soil because it was stripped away. The topography is going to be very, very flat, and because there's little topography, it means the gradient's going to be very low, and so that means water is going to naturally build up on the surface. So we're going to get lots and lots of lakes developing. So if we look here, here are a couple of examples of ice-scoured plains. This one's from Canada, this one's from Wisconsin, so you can see we have exposed bedrock, so that means there's no soil. We can see the bedrock itself actually looks quite smooth, and this is because it's been polished by the glacial movement. We can see that the topography is very, very flat, and this very flat topography is resulting in the buildup of large amounts of water, so we have lots and lots of lakes. Now, in terms of features associated with valley glaciers, so these are going to be in mountainous areas, we have the formation of cirques. So essentially a cirque is a bowl-shaped depression which forms on the edge of a topographic high, and you can see that in this cirque we're going to have a build-up of ice and snow. So this is where your glaciers are going to be starting, and we can see in this case we can actually see the glacier coming down. So here it is, it actually starts coming down the slope there, then it disappears off the bottom of the picture. Now, the movement of the glaciers along mountain valleys is going to produce a very distinctive valley shape, which we refer to as a U-shaped valley, sometimes also referred to as a U-shaped glacial trough. And so we can see a nice example right here. This particular one is from Norway. So you'll notice how the valley has a very distinct U-shape to it. And this is a very strong indicator that it's been formed by glaciers, because the glaciers will often leave quite steep near vertical faces on the sides of the valley, and then as you come into the valley bottom you have this broad concave surface, and then on the other side you have more near vertical faces, and it produces a shape that's like an uppercase letter U. And so both of these features are associated with mountain glaciers, valley glaciers. Now, the melting of the glacial ice produces a substantial quantity of water, and of course this water is going to go and form river systems and lakes. Now, the movement of the water will also allow the erosion of glacial till. So as the glacier ice melts, it's obviously going to deposit glacial till, and we can actually see in this picture down here, we can see the edge of a glacier. So the glacier is over on the right. We have sediment over here on the left, and you can see we have this line of material which is slightly darker in color here along the edge of the glacier. This is the moraine, and the moraine is made of glacial till. And so as the ice melts, obviously we're going to form large quantities of water. The water is naturally going to flow away. It's going to transport some of this glacial till with it, and so it's going to redistribute the glacial till from the moraine into a region in front of the glacier, and this region in front of the glacier is referred to as the outwash. Now, moraines are deposited at a glacier's terminus, where the glacier ends, and the moraines that form at the glacier terminus are referred to as end moraines. And end moraines come in two types. The first type is what's referred to as the terminal moraine, and the terminal moraine is the moraine that marks the maximum extent of the glaciers. So if we look at this picture up here, this is from the textbook, and it's showing us end moraines in green. Now, if we look at it, we can see that the end moraines are following a path that's coming around like so. In fact, I'm just going to mark it out there with a dashed red line. And so the presence of these moraines here shows us where the maximum extent of the glacial ice was. And so we know that these moraines are going to be the terminal moraines, because this is, this represents the maximum extent of the ice sheets. Now, the other types of moraines that we get, if you look here, are referred to as recessional moraines. So if we look behind the terminal moraine, you'll see there's lots and lots of other moraines, which are part of the glacial sequence. Now, these are referred to as recessional moraines, and these are produced as the glacier retreats. So as a glacier retreats, it's not a smooth retreat, it's a staged retreat. So the glacier will retreat for a while, and then it will stop. And when it stops, obviously that means it's going to have time to build up a moraine. Then the glacier will start retreating again, and then it will stop, and then it will build up another moraine. And then the glacier will start retreating again, then it will stop, and it will build up a third moraine, and so on. And so what you're seeing here are these moraines behind the terminal moraine here are recessional moraines produced as the glacier retreats. So the final type of moraine we have isn't a type of end moraine, it's actually referred to as a ground moraine. And a ground moraine is simply a layer of sediment that's deposited as the glacier retreats. So as I've been discussing, a end moraine can only form when the glacier stops. The glacier has to be stable for a period of time to allow a large quantity of glacial till to start building up to make a moraine. Now, if your glacier is retreating, it's obviously in motion. It's getting smaller. And so as your glacier is retreating, as the ice is melting, it's going to be dropping sediment. But because the glacier isn't stable, that sediment isn't going to build up in just one location. Instead, it's going to be spread all over the ground as the glacier retreats. And this is referred to as a ground moraine. And this is simply a layer of sediment that's deposited as the glacier is retreating. So it's a blanket of sediment that gets dropped. Now, within our ground moraine, there's often numerous ridges that run parallel to the glacier edge, and these mark very, very short pauses. So the glacier will retreat a little bit, it will pause for a very short period of time. That gives just enough time for a little ridge to build up, and then the glacier will start retreating again. It will pause for just a little bit of time, another little ridge will build up, and so on. And so it often gives a ground moraine an appearance, kind of a lumpy appearance, where you have one ridge after another. Now, obviously, the expanse and retreat of the ice sheets is going to have a very significant effect on sea levels. So at present, glacial ice contains about 28 to 35 million cubic kilometers of water, and this has all been derived from the oceans. So obviously, if all of this ice was to melt, all of that water would return to the ocean basins, and we would obviously have a rise in sea level. Now, during the maximum Pleistocene glaciation, we actually had somewhere in the region of about 70 million cubic kilometers of water locked in glacial ice, so pretty much double the amount we have now. And this would have been sufficient to lower the global sea level by about 120 to 130 meters. So we know that global sea levels during the Pleistocene would obviously have been a lot lower than at present. And these lower sea levels mean that large portions of what is now the modern continental shelf, so it's underwater, were exposed. And so this meant you could have walked across that land. And so during the last ice age, we had, for instance, the Bering Strait between Alaska and Russia was a land bridge. You could walk from one side to the other. The United Kingdom was joined to France because the English Channel wasn't around at that time because of sea levels. You had other things like Sri Lanka was joined to India. You had Papua New Guinea would have been joined to the northern coast of Australia, for instance, and this is all due to these low sea levels. Now, obviously, if we were to melt all the water that's held in glaciers now, that would lead to a sea level rise of about 70 meters. So this shows you just how extreme these changes in sea level can be when glacial ice is forming and melting. So if we look over here, we can see a diagram that's showing us changes in sea level throughout the last 200,000 years. Now, if you remember, of course, the Ice Age came to an end approximately 12,000 years ago. And so we're going to have the Ice Age ending about here. And obviously, when the Ice Age begins to end, we can begin to see we have an increase in global sea levels. And, that's not really a huge surprise. So as we come back here, we can see that when we're about 120,000 years ago, we can see we have some periods where we have the sea level rising, falling, rising, falling, rising, falling. And so these are essentially the result of these interglacials. And so when we have the sea level rising, that's showing us we have an interglacial, so we have glacial ice melting. And then we move into these troughs here. These are the periods of glacial expansion, and so this is obviously where seawater is getting locked up in the form of glacial ice and the sea level is dropping. Now, as mentioned, the weight of the ice sheets is going to have an effect on the continental crust, and this is going to lead to isostatic rebound. So this general process is referred to as isostasy. So the weight of the ice sheets that were covering North America, Europe and Asia literally pushed down the continental crust. They made it warp downwards. So that's just like you stepping onto a trampoline. The weight of your body is enough to cause the trampoline surface to warp down. Now, once the weight is removed from the continental crust, so once the ice melts, the crust is naturally going to behave in an elastic fashion, and it's going to want to bounce back up. Once again, just like you stepping off a trampoline. As soon as you step off it and remove your weight, the trampoline membrane is going to essentially snap back to its original position. So the continental crust is going to do the same thing, just on a much longer timescale. Now, the weight of the glacier pushed some areas of the continental crust 300 meters below their pre-glaciation levels. And so these areas are still rebounding even now. Because remember, the last ice age only finished 12,000 years ago. So that hasn't been a lot of time for the crust to bounce back up and try and return to its original height. Now, the effect of this rebound can be seen in certain features such as docks, which were built a few centuries ago and they were at the coast, can now in some cases be quite substantial distances from the coast because the ground has been rising up. So if we look here, we can see some of the isostatic rebounds. So just to show you this beach here. So this is a beach in Nunavut in Canada. So this area would have been covered in a very substantial ice sheet during the last ice age. And so what you can see is in this beach, we have lots and lots of ridges running approximately left to right. And these ridges essentially represent where the coastline was in the past. And so what you can see is over time, the land has been rising up, and so this has caused the sea to essentially slowly move down the beach, and we can see this downward movement in the form of these lines on the beach surface. Now, in terms of global isostatic rebound, where do we find most of it? Well, unsurprisingly, we find most of it in areas which were covered by substantial ice sheets during the last ice age. So we find it in areas such as Canada, Greenland, Scandinavia, a little bit in northern UK, so Scotland, and some of it in northern Asia. We also have a little bit of isostatic rebound down here in Antarctica, and this is a mixture of both the end of the last ice age and glacial ice melting in response to the increasing greenhouse gases, essentially producing global warming, which is our fault. Now, if we just zoom in on one area, we can see the isostatic rebound on a more local scale. And so just to make things easy, I went for a nice small country, so I went for the United Kingdom. So what we can see in here, this top diagram shows you the thickness of the ice covering the UK during the last ice age. And so you'll see most of Scotland, a bit of northern England, Wales, and a large portion of Ireland were covered to some degree by glacial ice, but the thickest portion of it was up here in Scotland, and so this is where most of the pressure is going to be from this glacial ice. So the continental crust which forms Scotland is going to have been pushed down by the weight of this ice, and so once the ice is gone, it's going to cause Scotland to bounce back up. And so what we can see when we look at this diagram here is we can see areas of the United Kingdom which are rising in green, areas which are stable in this kind of peachy orange color, and areas which are sinking in red. And so what's happened is you can think of the United Kingdom a little bit like a seesaw. So we had all the weight here in Scotland, and that pushed down the northern England and Scotland. But as soon as the ice is removed, it allows Scotland and northern England to start bouncing upwards, and this means that southern England must begin to sink in response. And so we can see that the United Kingdom is behaving a little bit like a seesaw there in response to the removal of the glacial ice. So the melting of the glaciers will obviously produce large amounts of water. Now, I'm not talking in terms of melting during the glacial retreat, I'm talking about melting of the glacial ice during the ice age. So obviously all that ice is going to start melting along the edge of the glacier. That's going to produce large amounts of water, which will form big rivers and in some cases quite large lakes. Now, during the Wisconsinian, this is about 85 to 11,000 years ago, we had many now arid parts of the United States, especially the southern states, had quite large lakes. So we know that this is in response to the pushing of the temperate band towards the south, but it's also going to be in response to large amounts of water being produced at the edge of the glacier when it's melting. Now, the wetter conditions and the melting of the glacial ice will lead to the formation of pluvial lakes. And these lakes are distal to the ice sheet, so they form far away from the ice sheet. Now, the existence of these pluvial lakes is a reflection of the cooler temperatures and the movement of the temperate zone to the south, and this results in cooler, wetter summers. Now, the existence of these pluvial lakes is inferred from several geologic features which we can see. So we can see things like wave-cut platforms or wave-cut cliffs. So this is essentially a vertical cliff face produced along the edge of these large lakes. We obviously have beach deposits because along the margin of these large lakes we're obviously going to form beaches. We have deltas, which represent where we have rivers entering these large lakes. We have lacustrine sediment, so these are the sediments which are actually being deposited in the lake. We have freshwater fossils, so we have lots and lots of freshwater organisms in these lakes. So we can see, for instance, lots of fish fossils that show us this must have been quite a large, quite productive body of water. And we also have the presence of evaporite. So when conditions start getting warmer after the end of the last ice age, we can begin to see the indications of the water which was in these lakes evaporating away. So if we look over here, we can see several of these pluvial lakes, and arguably the best known of them is Lake Bonneville, which is this large body of water right here. And Lake Bonneville is quite well known because the evaporation of Lake Bonneville related in the formation of the Great Salt Lake, which essentially is right next to Salt Lake City. So we can also see here we have Lake Manly, and Lake Manly is located in the area which we now refer to as Death Valley, which is of course the driest place on the surface of the earth. So you can see there's been quite a substantial change in climate in that area since the last ice age when compared to the present day. So yeah, the classic example of a pluvial lake is Lake Manly, which was located in modern day Death Valley. So the lake itself was 145 kilometers long and 180 meters deep, so it was a very substantial body of water. And when the ice age came to an end, obviously the amount of water entering the lake suddenly decreased, the climate became hotter and drier, and so that water is going to evaporate away, and it's going to leave behind evaporite deposits. And we can see the evaporite deposits right here in this kind of whitish pinkish tone. We can see some right here, we can see some right here, we can see a mixture of them within the valley right here, and these are all evaporite deposits which have formed due to the loss of Lake Manly. Now, in contrast, we have another type of lake which are called proglacial lakes, and these form proximal to the glacier. So these form at the glacier edge, and they form where meltwater accumulates along the glacier's margin. And the accumulation of the water could be due to a moraine, which essentially forms a barrier stopping the water escaping. Or it could be due to the glacier itself, because remember, the glacier's weight is naturally going to cause the crust to warp downwards, creating a topographic low. And so these topographic lows created by the glaciers can then fill with water, producing a proglacial lake. Now, arguably one of the best known glacial lakes is Lake Aziz. And it formed in this manner. So it was a proglacial lake, and it covered an area of approximately 250,000 square kilometers, and it covered areas of North Dakota, Manitoba, Saskatchewan, and Ontario. And so if we look here, there it is. You can see it's a very, very substantial body of water, and it's quite clearly located along the margin of the ice sheet. We can also see down here, of course, we have the Great Lakes as well. They are essentially proglacial lakes. Now, sediments deposited in proglacial lakes will range from muds to gravels, and this is a reflection of the poorly sorted sediment that's produced by glaciers. So remember, glacial ice contains sediment that ranges in size from clay-sized clasts all the way up to massive boulders. And so a lot of this sediment can become incorporated into the lake sediments deposited in these proglacial lakes. Now, one of the things that we see within these proglacial lake sediments is the formation of varves. So varves are light and dark bands. You can see them quite clearly. One band will be light in colour, then you'll have a darker band, a lighter band, a darker band, so on. And so each one of these couplets, these light dark bands, represents a year. The light bands represent the spring and the summer, and the dark bands represent the fall and the winter. And so this is quite helpful to us because it means we can work out the age of a lake simply by counting the varves. We can say, right, this lake was here for 100 years, 1,000 years, 10,000 years, etc. Now, the dark bands themselves have this dark colour because they're dominated by muddy sediment, and they also contain increased amounts of organic material. And this is because the lake during the winter periods would have been frozen. This means that the water would no longer have been in contact with the air, so the surface of the water would not have been being churned up by the wind. And if the water becomes very, very still, well, this means very, very fine sedimentary particles like clays and silts can begin to leave the water column and settle out onto the lake floor. At the same time, because during the winter, obviously the lake temperature is going to decrease, you're going to see an increase in the amount of animals dying, and so the organic material from those animals will get incorporated into the muddy sediments as well. And so the increase in the amount of mud and the increase in the amount of organic material is going to produce a darkening of the colour of the lake sediments. In contrast, during the summer, the lake water is being moved around by the wind. That means the water is being churned up. That means muds and clays find it more difficult to settle out of the water column. And of course, we also have decreased amounts of organic material going into the sediment because the animals are on the whole in much better condition, so they are less likely to die. So going back to the proglacial lakes, obviously the Great Lakes are a good example of proglacial lakes. Now, before the Great Lakes formed, the region was a flat lowland area cut by broad meandering rivers, so it was a big floodplain. Now, as the ice advanced as part of the last ice age, we begin to see that the area becomes heavily eroded. So the ice sheet comes across and it bulldozes the topography. It helps to flatten everything out completely. Now, because the ice sheet has so much weight, it's going to push down on the crust and cause it to warp downwards. And so as the ice sheet is moving forward, the weight of the ice is going to push the crust down, and the weight of the ice is also going to erode down as well. And so this is going to create several depressions, essentially 4 or 5 of them, which are going to form the modern day Great Lakes. And so if we just look at this diagram here for 14,000 years ago, you can see, for instance, we have this ice sheet sticking out, and we can see as this ice sheet pushes forward, the weight of it is going to push down the crust underneath it, but also the erosional force of the glacier itself is going to erode down. And so this is going to create a natural topographic low, which is going to fill with water later. Now, we need to remember that glaciers can erode below sea level because the weight of the glacier pushes the crust down. So the glacier is still going to erode, but the weight of it is pushing the crust downwards, and so this means the glaciers can produce topographic lows at levels below which rivers couldn't go. So a river can only erode to sea level. A river can't go below sea level. In contrast, a glacier, because it has the capacity to push the crust down as part of its process, it actually can erode to levels below sea level, creating very deep topographic lows which can fill with water later. Now, as the ice sheets retreat, obviously these topographic lows created by the ice will begin to fill with meltwater, and we will end up forming lakes. In this case, the lakes are located along the edge of the glacier, so these are going to be proglacial lakes. Now, obviously, there's going to be certain amounts of movement of the crust, so we're going to have isostatic rebound, and so this means over time the level of the land is going to change a little bit, and so this is going to cause some changes in the location and depth of water in some parts of these proglacial lakes. And so if we look here, we can see this diagram kind of summarizes the formation of the Great Lakes during the last ice age. So here we can see these are the Great Lakes here, and they're being formed by the movement of the ice over the area, pushing the crust down, eroding and creating these topographic lows. So obviously as the ice retreats, these topographic lows begin to fill with water, and then over time, as the ice sheet is retreated even more, the topographic lows have completely filled up with fresh water, and we have the Great Lakes. Of course, the Great Lakes drain into the Otter and St. Lawrence rivers, and then they'll go off towards the Atlantic coast. Now we can see that the location of the water will change over time because, of course, isostatic rebound will cause some areas which were covered by water to rise up above the lake level, at which point they'll obviously become dry land. Okay, so this is a good place to stop. So get up, have a walk around, get a glass of water, take 10 or 15 minutes to relax, and then please come back for part 3.